All right, so let's move to section 1.3. To start off section 1.3, I want to do an example where I give you the definition of the limit, and I give you an epsilon because it should work for all epsilons, and we're actually going to find the deltas that would work. And we're going to use that as an example to build up to proving that these limits actually exist. All right, so I've rewritten the problem, this time using the absolute value inequalities. Remember, they say the same thing, but I do want to show you two different ways of writing it. So we want to find the largest delta again, such that if our x's are within delta of 1, this is the punctured interval around 1 with delta as a radius, then our function values are within epsilon of, in this case, -3. You can think about if I plug in 1 into x squared minus 4, then I get -3. Okay, so that's my limit value. And this time we're given an epsilon of 0.25. You have to be given epsilon in these problems in order to begin. All right, so again, if I draw a little picture, so at at 1, we're -3, 0, 0, so we kind of have that going on. So we're looking at this point right here, 1, -3. We're given an epsilon of 0.25, so we're going to go a quarter above and a quarter below. So we're going to be at -3.25 on the bottom. We're going to be at -2.75 up top. So we need to bound this point within that epsilon band. So to find the upper value, so we need to find the upper. So we're going to have the function x squared minus 4 needs to be equal to -2.75. That's going to be the upper one. So if I add, that's going to give me x squared equal. All right, so I went ahead and solved for the upper bound and the lower bound. And so remember we're centered around 2. We're punctured, we can't be 2. Or sorry, no we're not, we're centered around 1. So remember we're centered around 1, and our upper is 1.118, and our lower is 0.866. So those look very close to being about the same, so of course this distance here is going to be 0.118. This distance below, and so the distance from here to 1 is 0.134, and it looks like the smallest of the two is going to be 0.188. So I'm going to pick delta to be that. So our answer is finally going to be choose delta equal to 0.118, and that will guarantee that we entrap -3 within an epsilon band that is within 0.25 above and below. Because remember, this one will be too far, in this case, it'll be enough on the bottom, but it's going to be too far to the top that you're going to jump outside your epsilon band and go above the value, which we don't want. We have to stay within 0.25 of our value.
Me again. So I have to stop and correct myself. There is something on the screen that is incorrect for the upper value. I'm sorry, for the lower value, the second line says x squared equals 0.25, and it should definitely say x equals 0.75. So that's another mistake on me, but I tried to do this all in one take, which with no script, which is a no-no for me. So lesson learned.
All right, so we want to get to the big point of section 1.3, and that's actually doing an epsilon delta proof of this limit. So when we prove it, we have to give a just argument that shows that no matter what epsilon I choose, there's going to be a delta that when my x's are inside my punctured interval around the x value, in this case we're going to use 4, then my function values are very close and stay close within epsilon of my limit value, which is 7. So we use a very formal way of doing this, and this is a formal proof. So anytime I begin a formal proof, I write the word proof. A lot of times you'll even say how you're proving this. That's a little more formal, but we're just going to say proof, sort of an algebraic proof. So we're going to start out just by writing basically the definition of what this should say. So this, we're kind of given that epsilon must be greater than 0. So remember, the definition says for all epsilon greater than 0. So that means no matter what epsilon I give, I should be able to find a delta, because it says for all epsilon greater than 0, there exists a delta. So that means I can choose a delta equal to something. Okay, and I'm going to leave it blank because the proof is that we're going to choose that delta so specifically and so nicely that it's going to work and the algebra is going to flow. So given the epsilon greater than 0, choose delta equal to something such that, and to do this type of proof, I have to use the absolute value inequality notation of the definition. So such that 0 is less than x minus the c value that I'm trying to approach, which is 4, is less than delta, such that, I'm sorry, I missed the word if. So if this is true, then the function value, which is 2x minus 1 minus the limit value, is going to be and stay less than epsilon. All right? So I want to do something with this, because what I need is, notice that I can choose delta to be something as long as it's less than absolute value of x minus 4, but I want it to be in terms of epsilon, because whatever epsilon I give you, delta needs to be in terms of epsilon to make that slick choice. So I'm going to go over here to the side and do a little bit of side work, because I'm going to simplify this, and some math magic's going to happen that when I simplify this, x minus the absolute value of x minus 4 is actually going to fall out in my algebra, and it's not by coincidence. If the limit exists, this process should work. So I'm going to come over here and I'm going to say the absolute value of 2x minus 1 minus 7, well, that's equal to the absolute value of 2x minus 8. But this has a common factor. I can pull out a 2. So the absolute value of 2 quantity, x minus 4, okay? And 2 is positive. Since 2 is positive, I can factor it out of the absolute value. So that's going to give me 2 absolute value of x minus 4. Well, there's my x minus 4. X minus 4, this thing, this expression right here, 2x minus 1 minus 7, had to have been less than epsilon, because that's the definition. So we say this is less than epsilon. Well, if I divide by 2 here, so I'm going to come down so that I keep good steps, not just go out of nowhere. So now I say 2 absolute value of x minus 4 is less than epsilon. If I divide by 2, and I get the absolute value of x minus 4 is less than epsilon over 2. Well, that means that if I let delta equal epsilon over 2, then x minus 4 will always be less than that. So what goes in my box is that epsilon over 2. So given epsilon over 2, I just need to, or sorry, given an epsilon, I just need to say, well, take half of it. That'll be my delta. If that's true, then we get this to also work. All right, so therefore, when 0 is less than x minus 4 is less than delta equal to epsilon over 2, then the absolute value of 2x minus 8, which is going to be equal to 2 absolute value of x minus 4, is going to be less than 2 times epsilon over 2, which is going to be equal to epsilon. Thus showing what I wanted to prove. So this is the formal proof, including the side work that justifies this, that the fact that this limit is actually 7. And you may think, well, that's obvious. But not necessarily, okay? Because if I would have had a corresponding picture, and I'm going to draw it in a different color, we didn't know that this, I could just plug in 4. For example, yes, we know that ultimately that looks like a line, y-intercept at -1 and a slope of 2. And so over here at 4, maybe we had a hole there. This was some function that created a hole, a rational function or expression that ended up creating a hole at 4, 7, which means that I need to be punctured here around it, some delta, and then now I can choose any epsilon I want, and immediately I just have to take half of it, and that delta will immediately work. So this proves that for any epsilon greater than 0, I have a specific delta that goes with it, and that specific one is half of it. All right, so let's do one that uses it involves a quadratic. We'll see that the process is very similar, and that the proof itself is quite boilerplate in that the wording is exactly the same. All right, so again, this is a formal proof, so we want to write the word proof. I'll write it closer to where I was because I'm going to have this side over here for that side work again. Okay, so again, I have to be given any epsilon, so I just go ahead and say given epsilon greater than 0, we're going to choose delta equal to something, okay? We're going to use the side work to get that something such that if, remember we've got to use the absolute value inequality notation, 0 is less than x minus 3 is less than delta, then the absolute value of x squared minus 6x plus 11 minus the limit value, which is 2, is less than epsilon. So I'm going to take this part right here, come over and do some side work to figure out how can I get this piece that I want. So if you look at the previous example, I'm going to have to get absolute value of x minus 3 to choose my delta. So let's go over here and write side work. Alright, so we got the absolute value of x squared minus 6x plus 11 minus 2 is going to give us actually plus 9. Now if I look at that in there, that is actually a perfect square trinomial. So that's actually the square of x minus 3. Okay, but what's great about all these values is that they're just square, which means that they're all positive. So no matter what, I can just say, okay, well that is the absolute value of x minus 3 quantity squared. So I can kind of like switch the absolute value and the square in this case because it's special. Well, okay, that means that x minus 3, remember, needs to be, in this case, less than epsilon, right? Because we're saying this is equal to this is equal to this, but this expression must be strictly less than epsilon. So if I want to solve for x minus 3, okay, then at that point, the absolute value of x minus 3 squared is less than epsilon. I can take the square root of both sides. I'm sorry, epsilon, not 3. I get the absolute value of x minus 3 is less than the square root of epsilon. Okay, well that means this is like my delta, right? Or this has to be less than delta. So that means this needs to be my delta. So choose delta equal to the square root of epsilon. And then we continue. Therefore, if we choose delta equal to the square root of epsilon, then if 0 is less than the absolute value of x minus 3 is less than delta equal to the square root of epsilon, then the absolute value of x squared minus 6x, I'm going to go ahead and write that as plus 9, which equals over here the absolute value of x minus 3 squared. But we said, okay, well that has to be less than, replacing this with delta, okay, that gives us the square root of epsilon quantity squared, which is equal to epsilon. So we said that this expression therefore must be strictly less than epsilon, thus showing what we wanted to prove. So again, no matter my choice of epsilon, as long as it's positive, which in this case is really important because we're talking about the square root, as long as it is positive, I just need to take the square root of epsilon and I end up getting a delta that will always work for this case. So we're showing that for all epsilon greater than 0, we have found a delta that works such that when this is true, this is also true, which completely proves this even at points of, dare I say, discontinuities. Okay? So this is a very strong argument. Actually, it is the most formal argument for the fact that this limit not only is true, but exists in this case.